Welcome to physics. Looks like things are going to be a little bit different, at least for the next few weeks. So the plan is for science classes to post assignments and content on Tuesdays and Thursdays. So my plan is to post a brief video, sometimes an interactive exploration like you'll have today, and then an assignment. And these things may change as they go along. And then I'll have office hours on Fridays, and then also be available anytime. You can reach me through email, and we can set up an online discussion or whatnot at any time. So you just have to give me feedback and let me know. So last time we met, we were finishing up the theories of what light is. And as I told you, we're going to transition into refraction. Now, chapter 14, refraction, we already defined refraction in the chapter on waves. So just kind of recapping, refraction is a bending of light. It has to pass from one substance into another substance. So in the diagram that we have here over to the right, we have light going from air into glass, and then back into air over here. So it goes from air, it's traveling in this direction. When it goes into glass, it changes directions. Remember, we talked about that change in direction being caused by a change in speed. So the light is either speeding up or it is slowing down, and that change in speed causes that bend, that change in direction, and that change in direction is refraction. Diagrammed in terms of waves, you see in this diagram the direction of the initial wave here, traveling along this way, and it goes into the second substance. And when it goes into the second substance, it changes in direction. But as you can see, that change in direction is not the only thing that changes. If you notice the spaces between our wave fronts and the different substances, that would be your wavelength. And so not only does the direction change, but the wavelength also changes. And as we said previously, the speed of the wave changes. So these things change. The one thing that does not change is the frequency of that light. That frequency of the light, if it changed, then frequency corresponds to color, and things would appear significantly different colors underwater, and they do not. Now, the amount of change is really going to depend on the change, or the amount of bend is going to depend on the change in speed, and a number we can use to be able to talk about that change in speed is index of refraction. So in this diagram, we have a light going from a low index of refraction into a high index of refraction, and we see the amount of bend. Now, index of refraction then is basically a value that describes how much the speed changes, and by that, how much bend you would expect. So then we define the index of refraction as the ratio of the speed of light in a vacuum to the speed of light in whatever your substance is. Okay, so then the symbol for the index of refraction is a capital N. Speed of light in a vacuum to the speed of light in the substance. Now, in symbols, N is your index of refraction, C is the speed of light in a vacuum, V is the speed of light in your substance. We know from the nuclear chapter that the speed of light in a vacuum is 3 times 10 to the 8th meters per second. Now, thinking in terms of units, speed of light a speed over a speed, meters per second over meters per second divide out. And so in terms of units, the index of refraction has no units to it. Okay, the lowest value you can possibly get for the index of refraction would be 1. And that would occur if you had the speed of light not change from a vacuum. You would just have c over c, or 1. Realistically, these values will range from 1 up to about 2.5. So you're not looking at a very large range of different indices of refraction. So then let's consider an example. Okay, calculate the speed of light in water. Well, we can do that using our equation, n equals c over v. In the table over here, we have different indexes of refraction for the various different substances. Okay, in general, as that index refraction value goes up, most of these, they're not quite in order, but as the value gets higher, the speed changes more, and as the speed changes more, the bend is going to be greater. So then on part A, to calculate the speed, we are in water, and so the index of refraction of water is a 1.333, so that goes in for our n. C over v, c is the speed of light, 3 times 10 to the 8th meters per second over v. So then algebraically, when we solve down, we get 3 times 10 to the 8th meters per second divided by the 1.333, which is going to give us a speed of light of 2.25 times 10 to the 8th meters per second. So then when light is in water, it's not traveling 3 times 10 to the 8th. It slows down to 2.25 times 10 to the 8th meters per second, which means it will refract, it will bend. In part B, compare in equal periods of time, okay, how light will travel in air and water. Well, if we consider air and we consider water, if we just use a simple time period like 1 second, when 1 second at 3 times 10 to the 8th meters per second, light's going to travel 3 times 10 to the 8th meters, but in water, it's only going to travel 2.25 times 10 to the 8th meters. Okay, so that light does not travel as far when it's in water. Now, because light doesn't travel as far when it's in water, it causes us oftentimes to misjudge distances. If you're looking at something that is underwater, it's very easy to look at it and think that it is actually closer than it is. If you've ever been to a lake, the ocean, somewhere that the water is reasonably clear and calm, you can look down under the water and the bottom or things underwater appear much closer than they are. This is illustrated in this picture. This is a picture from National Geographic magazine that was published about 7 years ago. A lake called Flathead Lake in Montana, very high up in elevation and very clear water. The lake is actually 370 feet deep. Now, the portion we're looking at, it's not quite 370 feet deep here, but it is much deeper than it looks to be. So the person floating on the raft there looks like she could just hop off the raft and swim down to the bottom. It would be quite a challenge to swim down to the bottom because it is quite deeper. The bottom looks much closer. We misperceive how deep the water is because we're used to judging distances with light traveling in air, and light doesn't travel as fast in water, so we misjudge things to be closer than they actually are. Couple other pictures of this lake. In the top there's a diver, notice in full bodysuit, full wetsuit, because the water is quite cold, and that's why it is so clear. And then over on the right side toward the bottom, a boat that literally looks like it's just floating in air, but it's actually floating on the water. okay, the very clear water allow us to make this observation that things actually appear closer when they're underwater. We misjudge the distance. Along with misjudging the distance, when light bends, we often misjudge where things are, as in this picture right here. Head or body, which are you seeing in its actual location? Now, if you think about it, you're judging things accurately through air. And so for you to see the person, the man's head, light reflects off his head and goes into your eyes through air. So his head and his hand and the physics is fun sign, you're seeing at their actual locations. The light that's coming into your eyes from his body is traveling, reflecting off of his body through water. And then when it exits the water into air, it bends. And because of this bend, you see that body not where it's actually located, because the light goes into your eyes and your mind follows that light straight. It can't see around corners, okay? It doesn't see the bend, it follows it straight. So you perceive his body not in the actual location where it is because of this bend, okay? Now, kind of summarizing, bent pencil on the left side. So the pencil's going down when it's in air. And when it's in air, it's along this direction here. When it goes into water, it bends. So again, in air, it's along that direction. In water, it looks like it's along that direction. The actual pencil is straight. It's the light that is bending, causing you to misperceive where the bottom of the pencil is. Illustrated in the diagram to the right, you see the top of the pencil up here, okay? But the bottom of the pencil, the actual bottom of the pencil right there, but the light coming from that bottom goes from the water up into air, and when it goes into air, it bends. Okay, and when it bends and goes into your eyes, your mind doesn't follow the bend back. It follows these rays right here and here straight back, and it sees those rays come together, and so it perceives the end of the pencil much closer to the surface and also shifted over to the side. So when you're looking at things underwater, this refraction causes you to see things closer and shifted off to the side. Now, Snell's Law. Index of refraction so far, we've said n is equal to c over v. And n is equal to c over v, the bit larger the n value, larger that index of refraction, the greater the change in speed. And that greater change in speed means a greater bend or change in direction of that light. Now, the disadvantage of that is it doesn't tell us how much it bends. Okay, so Snell's Law is going to utilize the index of refraction. Okay, but it's also going to allow us to calculate angles. So if I draw a boundary, here's my boundary between air and, let's say, water. And if I draw a ray of light going from air down into water, I'm going to change to a different color. There's a ray of light coming down from air incident on the water. Now, the angles here, when we measure the angles, those angles are going to be measured from the normal to the surface. So I'm going to draw a line in perpendicular. And so then my angle of incidence, theta I, would be right there. when that light goes down into water, it changes direction. So then I'm going to draw in theta r right there. Theta I is between the initial light, the incident light, and the normal. Theta r is between the refracted light and the normal. Okay, these angles are not equal to each other. To be able to calculate these angles, basically based on the geometry and a derivation, which I'm not going to go through now, okay, the top substance we would say has an index of refraction of n1. The bottom substance index of refraction of n2. And so then Snell's law basically says that the index of refraction times the sine of the angle is constant. So n1 multiplied by sine theta 1 is equal to n2 multiplied by sine theta 2. The index of refraction multiplied by the sine of the angle in that substance is equal to the index of refraction in the second substance multiplied by the sine of the angle in that second substance. So let's apply this back to our physics teacher photo there. Light reflects off the man's body and makes an angle of incidence in the water of 22 degrees. We want to calculate the angle of refraction the light makes in the air. Okay, so then if we think about the light coming off the man's body, the diagram down here at the bottom, make sure you understand this is a top view. So you're up in a tree looking down on the top of the man's head. Okay, and so the light is actually coming from his body, traveling in the water, and then it goes into air. That's very important to identify. So on part A, our light is starting off in water and it's going into air. So then when we apply Snell's law, n1 sine theta 1 is equal to n2 sine theta 2. Then on the initial side, everything deals with water. On the second side, everything deals with air. So then we plug in values. N1, that would be the index of refraction of water. From your table down there at the bottom, that's 1.333. Sine, the angle made in water happens to be the angle of incidence, and that's 22 degrees. Sine of 22 degrees. N2, your second substance is air. Looking down at the table, the index of refraction of air, 1.000293. And the angle that would be made in air would be an angle of refraction. We don't know that value, so I'm going to put sine theta r. Now, mathematically solving down for this, you're going to take 1.333 multiplied by the sine of 22, and then divide that by the 1.000293, and then take the inverse sine. So when you solve down mathematically, we're going to get a value of 29.95 degrees. Now, 29.95 degrees compared to the original angle of 22 degrees, that means that the light is going to bend outward. It's going to bend away from the normal. So then if I draw that on our diagram at the bottom, I need to go to a bigger angle. So I'm going to draw the refracted ray over here so that this angle right there, that's the 29.95 degrees. Now, why do you see the man where you do in the water? I'm going to put this all in green. That light would have to go into your eyes. So this is you, and that light's going into your eyes. When it goes into your eyes, your mind follows it straight back. And when it follows it straight back, okay, all back along here. It doesn't see the bend. It follows it back over here. And so then you see right over here the man's body. His head you're seeing in the actual position because that light's coming through air, but his body, the light's coming through water. And so just as we talked about a few minutes ago, it is appearing shifted closer, and it is also shifted to the side. Now, the rest of what you're doing today is going through an investigation to understand this refraction a little bit more, and that's part of a simulation online, and then also a Google form that will kind of guide you through. And then there are problems that are also in the assignment that are linked